Throughout the next 4 lessons, we're going to be talking about the same idea, and that is going to be solving systems of equations or inequalities. Before we get started on the mathematics of solving those systems, I'd like to give you an analogy today, which is the same sort of idea, but in the real world. So here it is. Let's say you wanted to buy a car. A lot of us need a car or want a car. Let's say you're buying a car and you have a few things you want to make sure this car is like. Maybe you want the color of the car to be red, for example. You also want the car to have really good gas mileage. Maybe you want it to have at least 30 miles to the gallon, for example. And you don't want to spend too much on this car, so maybe you set the limit of your cost at something like $25,000. So you want a red car, you want it to have this gas mileage, and you want to make sure that the cost isn't too high. Now, that's a problem. It's a real world problem, really. And you want to solve that problem by finding a car. Now, the wrong way to solve that is to go out and buy one red car, and then a second car that gets really good gas mileage, and then a third car that doesn't cost very much. That's really not satisfying your problem. It's not solving your problem. The solution to this problem is to find one car that is red and gets really good gas mileage and costs less than $25,000. That one car would solve that problem. Well, that idea of one thing solving a bunch of different problems at the same time is the same idea behind solving a system of equations. And so that's what we'll talk about today and for the next few lessons. We'll talk about solving systems of equations and inequalities where one set of numbers will satisfy all of the problems at once. So let's define a few terms as we get started with the math today. A set of 2 or more linear equations form a system of linear equations. So just like the cost of the car and the color of the car were 2 different things, here we're going to have 2 different equations that are going to form a system of linear equations. We say that an ordered pair of numbers that makes all of those equations true is called a solution of the system. Just like one car, which is red and doesn't cost very much and gets good gas mileage, that one car would have been a solution of your original problem. So for example, y equals 2x minus 5 and y equals x minus 2 is a system of 2 linear equations. A solution of this system is actually the set of numbers x equals 3 and y equals 1, or the ordered pair 3, 1. Now to check to make sure that really is a solution, we can confirm it by plugging in these numbers into each of the equations to make sure that everything is true. So, for example, with the first equation, we would have plugged in 1 for y and 3 for x, and we would have the equation 1 equals 2 times 3 minus 5, or 1 equals 6 minus 5, or 1 equals 1. And that's true. But we haven't confirmed yet that 3, 1 is a solution of the whole system until we make sure it also satisfies the other equation, the second equation. If we plug in 1 for y and 3 for x into that equation, we will have 1 equals 3 minus 2, or 1 equals 1. And again, that's a true statement, that 1 equals 1. And now we can say that 3, 1 really is a solution of our system. Now, systems of linear equations, they arise very naturally. And we'll see a few problems later on to demonstrate this. But for now, the biggest question that you and I need to answer is this. If we're given a system of 2 linear equations with 2 unknown variables like x or y, how would we find the solution? Did you notice that in the work we just did, I gave you the solution? I actually told you that 3 for x and 1 for y was the solution. We just checked to make sure that it really worked. Now we need to figure out how to find that solution, how to find the x equals 3 and y equals 1, like we did in the last example. So in this lesson, we're going to learn about a very special technique for solving systems of two linear equations, and it's called solving by graphing. Now, to start talking about solving these kinds of systems by graphing, we need to ask a very special question. From a graphical perspective, from a visual perspective, what does a solution to the system y equals 2x minus 5 and y equals x minus 2 look like? I mean, what does the solution really mean from a visual perspective? Well, the solution needs to be a point on each of the two lines. Remember, that point has to satisfy the first equation and it has to satisfy the second equation. So it has to be on both of the lines, and it needs to be the same point on both lines. Just like one car and the same car had to satisfy all the different criteria. So, how can you be a point on two different lines but be that same point? The answer is you must be an intersection point of the two lines. So, when we're looking for a solution of a system of linear equations, what we're doing is looking for an intersection point between the two lines. And that's what solving by graphing is going to do. It's going to look for intersection points once we graph the two lines. So let's solve a system that we've mentioned a few times by now and do it by graphing. So this is the system I talked about a moment ago. The technique is pretty straightforward. We graph the two lines that we had and we find their intersection point. So if you look at the graph, we have two lines. One has a y-intercept of -2. That's going to be the one for the equation x minus 2, or y equals x minus 2. And the other has a y-intercept at -5, and that's going to be the line that corresponds to the equation y equals 2x minus 5. Now, if we've drawn the graphs carefully, we see an intersection point, and it looks like that point occurs at 3, 1. So we see from the sketch that that intersection point really is at 3, 1. That's the solution. But in order to really be sure, we still needed to plug in 3 for x and 1 for y in the original equations to make sure we were right. We did that a moment ago, so we know we're good to go here. Now, before we move on to some other examples of systems of equations, let me share just a bit of terminology here. When a system has a unique solution, just like the example we just did, where x equals 3 and y equals 1 were exactly the solution, we say that such a system of linear equations is an independent system. So if you have one unique solution as a system, you're called an independent system. Now, before we move to our next example, let me make a comment here that's extremely important, I believe, when we're solving by graphing. You should notice that something like graph paper or grid paper would probably be really smart to use for these problems. Why is that? Because you're going to want to be very, very accurate if you're going to try to spot exactly where that intersection point is. If the answer's 3, 1, you don't want to look at it, visualize it, and guess 2, 1 or 3, 0.7 or something like that. You really want to see it as 3, 1. So some graph paper or grid paper would be very, very helpful in this lesson. And secondly, it would probably be very, very smart to check your solutions when you're solving by graphing, just to make sure you're right. What do I mean by that? Remember, to check your solutions means you plug the numbers back into the original equations to make sure that everything is true. So in this lesson especially, you're really going to want to spend the time to check your solutions, to work with the equations and plug in the numbers, just to make sure that you've gotten everything right. Now, I would suggest that at this point, you take a sheet of graph paper or grid paper and you try the following example yourself, and then we'll check back together in a moment to make sure you got it right. Here's the example. Solve the following system of two linear equations by using graphing. Y equals -4x plus 3 and y equals 3x minus 11. Okay, did you get a solution? Let's check. Let's work it together and make sure. Now, before we actually check, let me point something out here. Notice that we know that there has to be a solution of this example before we ever get started with the drawing. Can you think about why? Look at the slopes of those equations for just a second. Well, one of them has a slope which is negative, and the other one has a slope which is positive. So if you think about it just for a second from a critical thinking perspective, one of the lines, the line with positive slope, is going to go up like this, and the other line is going to be going like this, the one that has negative slope. These two lines must cross somewhere. And remember, it's that intersection point that you want, which gives you the solution. So we know there is going to be a solution here, and now the question is, can we find it? Well, if you draw those two graphs, which are going to be two straight lines, you're going to see that there is an intersection point, and it looks like it happens at about 2, -5. Is that the point that you found? X equals 2 and y equals -5? Well, if you did, you're in good shape, but let's make sure that that really is the solution. We go back to our two original equations, and we plug in x equals 2 and y equals -5, and we see if everything works out. So the first equation was y equals -4x plus 3. Plugging in x equals 2 and y equals -5 gives me -5 equals -4 times 2 plus 3. And on the right-hand side, that's the same as -8 plus 3, using our order of operations a bit, doing the multiplication first. And -8 plus 3 really is -5. So I have the equation -5 equals -5. Of course, that's true. Now we try the same numbers again with the second equation, y equals 3x minus 11. Plugging in 2 for x and -5 for y gives me -5 equals 3 times 2 minus 11, or 6 minus 11, or -5. So I have -5 equals -5 again. Of course that's true. And so we've now confirmed that 2, -5, or x equals 2 and y equals -5, really is a solution of the system, because that information took care of both the first equation and the second equation. It made both of those equations true. And remember, it's good to think ahead just a bit, as we did a moment ago, to make sure that you really will have a solution. If one of the slopes was positive and another one was negative, then you're guaranteed that there's going to be a solution somewhere, and your problem then is just to find it, which is exactly what we did a moment ago. Now, here's another question that we should really ask. Could there have been any other solutions to the system of equations that we just studied? This is a good question. Maybe there's a second solution somewhere else. Well, let's think about this for a second. We're dealing with straight lines in this lesson, and the equations that we're dealing with are the equations of straight lines. So if you have one line going in one direction and another going in the other, and you have an intersection point, there won't be any other intersections later on, because one of the lines is just going to keep going up, and that other line is just going to keep going down. They're never going to intersect anywhere else. So we were guaranteed in this example that there would only be one solution. And if you remember the terminology we used a few minutes ago, that means that the example we just did was an example of an independent system of equations. So there were no other solutions to that system at all. All right, let's move to another example. I think it's very good to keep working through these and to make sure we've got all of this settled. So let's solve the following system by graphing again. The system of equations will be 3x plus 2y equals 5, and 6x plus 4y equals 19. Now, we see here two equations. They're both the equations of lines, but they're in standard form. They're not in point-slope or slope-intercept form like we talked a few lessons ago. So we need to convert both of these equations into something like slope-intercept form or point-slope form before we actually draw the lines. At least that would make it easier. So let's try to convert those into slope-intercept form and see if we can finish the problem for there. Now, slope-intercept form, remember, is y equals mx plus b, where m is the slope and b is the y-intercept. So we really want to solve that system and convert those equations into that form if we can. Now, we go from 3x plus 2y equals 5 and 6x plus 4y equals 19 into these converted equations. So let's walk through that together. Let's take that first equation, 3x plus 2y equals 5. Subtracting 3x from both sides gives me 2y equals negative 3x plus 5. And dividing both sides by 2 gives me y equals negative 3 halves x plus 5 halves. Hey, that's in slope-intercept form. Perfect. Let's set that aside now for just a second and look at the second equation. 6x plus 4y equals 19. Subtracting the 6x from both sides gives me 4y equals negative 6x plus 19. And dividing by 4 gives me y equals negative 3 halves x plus 19 over 4. So the original system that we started with is the same as the system y equals negative 3 halves x plus 5 halves, and y equals negative 3 halves x plus 19 over 4. Now, what do you notice about those two equations? Well, they both have the same slope, don't they? But they have different y-intercepts. What does that mean about the graphs of the two lines? Well, it means that they're parallel. And what does that mean about their intersection points then? Well, the answer is they're not going to intersect one another. They both have slope negative 3 halves, and they're just going to stay parallel the whole way, no intersection, and that means that there is no solution of the original system that we started with because those lines are parallel. Now, we should talk about a little bit of terminology here just to make sure we get this down. The example I just showed you had no solutions. That's the first example we've seen like that. And anytime you have a system of equations that has no solutions, we're going to call it an inconsistent system. So that's a second word or second phrase we need to remember. If a system has no solutions, we call it an inconsistent system. Now, let's go on to another example. It looks pretty innocent at first. It turns out to be pretty interesting. So let's take the following system and solve it by graphing. Y equals 4x plus 3 and 24x minus 6y equals negative 18. Go ahead and try to solve that yourself. Now, if you tried that and you did it correctly, you're probably smiling a bit as you look at this example. It's a unique example. Let's walk through it together. Okay, the first of the two equations is already in slope-intercept form, so you can graph that line immediately and not worry about it. Let's look at the second equation and rewrite it in slope-intercept form. It's straightforward to do. Once we've rewritten it, we can draw the graph. So we started with 24x minus 6y equals negative 18. Subtracting the 24x on both sides gives me negative 6y equals negative 24x minus 18. And now if you divide by negative 6, you get y equals positive 4x plus 3. Remember, when you divide both sides by negative 6, a negative divided by a negative gives you a positive. So the equation here is equivalent to y equals 4x plus 3. But now look at the two equations you have. They're actually the same equation. Now what does that mean then about the system of equations we started with? It turns out that instead of being two different lines, they were actually the same line. There's one line right on top of the other. Now, what does that mean about solutions of the system? Well, it means that not only is there one intersection point, there's actually infinitely many different intersection points because every point on both lines will be an intersection point. So in this case, when the two lines intersect one another everywhere, we're going to say that the solution set is actually the set of all real numbers. You can think of the two lines as simply laying one on top of the other. And when you work through that and you see a system like this, it's very special. And we're going to have a different name for that sort of a system. When a system has infinitely many solutions, because the two lines are actually the same line, we're going to call it a dependent system. Now, the examples of systems where two linear equations with two variables really fall into three categories now. I've shown you actually all three types of systems that you can have. Let's just review them very quickly. You might have no solutions. No solutions means that the two lines are actually parallel with one another. Do you remember what we called that? We call that an inconsistent system. You might have infinitely many solutions, which means the two lines are actually just one and the same line, and that's known as a dependent system. Those two things are interesting, but the case we really care about the most is when the system actually has exactly one solution, when the two lines just cross at one point. And remember what those are called? Those are called independent systems. And now let me emphasize this. Any system of two linear equations that you study has to fall into one of those three possibilities. There are no other possibilities, either zero solutions, infinitely many solutions, or exactly one. That's the only three possibilities we have. Now, I'd like to look at another example where there's just one solution to the system. I think that's important to do as we move forward in this lesson, because really it's these independent systems that are of most importance and the ones that we're going to see most often. So here's the example I want us to think about. Solve the following system of equations with graphing. Well, the system of equations is going to be pretty simple, actually. Y equals 7 and x equals 4. Now, when you first see that system of equations, you might be thinking something like, wait a minute, are those really representing lines? I mean, y equals 7 just sounds like y, a number, equals 7, and x equals 4 is the same. Are those missing one of the variables? Don't I need some x's and some y's in both of the equations? Well, that reaction, if you had it, would be very understandable. But if you pause and think for just a second, you realize that y equals 7 and x equals 4 actually are the equations of lines. It's just that they're equations of very special lines. So let's think back a few lessons and think about what these equations actually mean. In the Cartesian plane, or the xy plane, the x and y plane, y equals 7 really is an equation of a line, and it's the equation of the line which is horizontal and has a y-intercept at 7. So it's the line that goes through points like 0, 7, and 3, 7, and -5, 7. It goes through all the points where the y-coordinate is 7. So it's that horizontal line. Okay, so that's how we would start with graphing there. What about the line that's given by the equation x equals 4? Well, we've run into this kind of an equation before as well. It's simply the line that goes through all the points where the x-coordinates are all equal to 4. You know, points like 4, 0, and 4, 2, and 4, 8, and 4, -5, and so on. If you plot a couple of those points and you draw the line that connects them, you're going to see that you get a very special line again. It's now a vertical line. So anytime you see an equation like x equals 4, or x equals 9, or x equals -3, you should think vertical line. Now, if you plot those two lines in the plane and you look for a solution of that system of equations, will you get an intersection point? Well, try it yourself and see what you get. Okay, what did you get? Well, it turns out that you really do get an intersection point, right? You've got a horizontal line and you've got a vertical line. Those have to meet. And they meet, in this example, at the point 4, 7, or x equals 4 and y equals 7. And therefore, the system of equations that we started with has only one solution, 4, 7, and that means this is an independent system. Now, we've seen several examples today of solving systems of two linear equations with two unknowns. I've used the unknowns or variables x and y most often. We could have actually solved systems with other variables, a and b, or s and t. We could have made up all sorts of names for those unknowns. We often will use x and y to remind us of the xy plane, so that the solving by graphing will allow us to see that intersection point most naturally. Keep in mind, though, we will be allowed to use other unknowns or other variables later on. Now, it turns out that this method by graphing, which is really fun and really cool, very visual, has some drawbacks. And so as we close this lesson, I'd like to talk about a couple of those drawbacks, those negatives, if you will, about solving by graphing. First of all, what if I decided to look at a system of 3 linear equations with 3 unknowns or variables? So, just so you know, lots of people want to actually look at this kind of thing in their work. So it's not a really crazy or bizarre idea to think about 3 equations and 3 unknowns. What would it mean to try to solve that system of equations by graphing? Well, it means that we'd have to draw 3 different lines in 3-dimensional space. So not just the XY plane, but the actual space that you and I live in, X, Y, and maybe Z as the 3 variables. That can be pretty difficult for some people to visualize. And I personally would not suggest solving that system by graphing. And you might say, well, I could have handled that. 3 dimensions wouldn't have been hard for me. I could have drawn that. Well, what if I up the ante a bit and I want to solve a system of 4 linear equations with 4 unknowns? Really, that's a very natural question to ask. And at that point, it could be very hard to draw lines in 4-dimensional space. In fact, it makes no sense to me what that would mean. So the method of graphing is limited in that it really only works in, say, 2 dimensions, X and Y, in the XY plane. And for some people, it works pretty well in 3 dimensions. But beyond that, the method of graphing, solving by graphing, is really limited. But that's actually not the only reason that the method of graphing is a bit on the downside or the negative side. A second drawback is that it's sometimes difficult to pinpoint what the exact solution of the system is, or to pinpoint where that intersection point really occurs. For example, take this system of linear equations. 3x plus 5y equals 7, and 2x minus 4y equals 7. It's actually a fairly innocent looking system. It's got all whole numbers for the values inside the equations. But guess what? The solution to that system is x equals 63 over 22 and y equals negative 7 over 22. Let's be honest. If you were drawing those 2 lines on graph paper and you tried to pinpoint exactly the intersection point as 63 over 22 and negative 7 over 22, it would be impossible to determine that that's the exact point for that intersection. So even with really good graph paper and really good eyes, it would be very difficult to identify that specific point. So with these 2 drawbacks in mind, I'm going to suggest that we should come up with a second, different approach to solving these kinds of systems of linear equations. Even if it's just 2 equations, I'd like for us to come up with an alternative approach for solving those systems. Thankfully, those approaches exist. And in the next lesson, we'll talk about exactly that.